The spectra of gas and stars in the central regions of galaxies reveals that most, if not all, bright galaxies harbor a supermassive black hole at their center. For instance, M31, the Andromeda galaxy, has a black hole with mass of over 10 times the mass of our own galaxy's supermassive black hole. Now, even though the masses of these black holes are large, they are difficult to measure. The observable effect of the black hole dominates the dynamics of gas and dust only on the very smallest scales, thus requiring high angular resolution for accurate measurements. To determine how close we need to get, we calculated the distance over which the gravitational potential of the black hole dominates over the gravitational potential of the surrounding stars. We can define the radius of influence of the black hole. The radius of influence of the central supermassive black hole is essentially the radius equivalent to the escape velocity, where the velocity is the velocity dispersion of the stars in the bulge of the galaxy. That's sigma star. Writing these in terms of units appropriate to the problem means measuring the mass of the black hole in terms of 10 to the 8 solar masses and the velocity in terms of 200 kilometers per second. The radius of influence of the black hole is about 10 parsecs. So black hole masses have been measured by modeling the dynamics of stars or gas disks in galaxies in which this radius of influence is resolvable, which in practice means resolvable with the Hubble Space Telescope. The first good evidence for a massive black hole in the center of a galaxy was from M87. So this is M87. You see the central luminous object and the relativistic jet. This is Hubble's tuning fork galaxy classification. M87 is an E0 galaxy and became very, very known to the general public also last year because the Event Horizon Telescope imaged the event horizon of the central supermassive black hole. So M87 was the first object for which the nuclear gas disk was used to determine the central mass. The first observations with the Hubble Space Telescope could determine the velocities at a distance of about 0.25 arc seconds, so about 20 parsecs away from the center, and found velocities of about 1,000 kilometers per second on either side of the center mass. The velocities were consistent with Keplerian motion about a central mass of mass 2 billion solar masses. Now, generally speaking, elliptical galaxies have a central black hole whose mass is proportional to the galaxy luminosity. You're seeing here is a correlation between the mass of the central massive black hole and the luminosity of the bulge. There is also a tight correlation between the mass of the central supermassive black hole and the velocity dispersion of the stars. It is not really surprising that big galaxies should have big black holes. What is surprising, though, is the tight correlation between the mass of the supermassive black hole and the velocity dispersion. Because when the velocity dispersion is measured, it is dominated by stars that are far enough out that they are outside the radius of influence of the supermassive black hole. So these stars here with larger velocity dispersion, they are outside of the radius of influence of the black hole. Why a black hole mass should be so tightly correlated with the velocity of stars that are ignorant of the existence of the black hole is an unanswered question.